Welcome to the 7.5 episode in a series for calculating pi on my relay computer. This one picks up where we left off in episode 7, so if you haven't seen that one, then it might be worth a watch. But if you're familiar with non-restoring binary long division, then welcome, we've been expecting you. And here's where we got to, non-restoring division, bent and twisted to fit within the confines of my relay computer, and all ready for coding up in assembly. Now, if you're looking at the screen thinking, what's this monstrosity? Then I really recommend taking a look at episode 7 to help make sense of all of this. If you've already watched episode 7 and are still thinking this looks like a monstrosity, then rude. But hopefully as I start coding this up, it'll come to life a bit. And spoilers, I have a sneaking suspicion this isn't going to win any speedruns, so we'll more than likely be making optimisations and perhaps even simplifying things a bit. Before we get into that though, I want to take a quick aside for what episode 7 meant for our pi pseudocode and shopping list. Usually around this point we get to this slide in the series recap, and at the bottom right is our shopping list, the list of operations that aren't native to my relay computer and we didn't approach designing and coding up. We are of course currently trying to tick off long division, except it's not long division we're doing anymore, but a long reciprocal. So our 4 BBP fractions will start in the first iteration with 1 divided by 1, 1 divided by 4, 1 by 5 and 1 by 6, which are effectively reciprocals of 1, 4, 5 and 6 respectively. We can then left shift A 2 places to get 4 divided by 1 and left shift B 1 place for 2 divided by 4. Speaking of shifting tricks, we don't need a long right shift anymore, so that can come off the shopping list now. And that's because, as we saw last episode, we can offset our reciprocal and effectively bit shift the result. So to quickly visualise that, here's the build-up of 1 over 125 that we worked through in excruciating detail. As we saw, each iteration of our reciprocal algorithm adds an extra bit of accuracy to the result, and effectively shifts the result left 1 place from the previous result. At the end here, we have the 4-byte result as wanted, for 1 over 125. But 4 rows up, we also have this, which comparably has the hex result shifted 1 place to the right because the binary result is comparably shifted 4 places. In the BBP pseudocode, we need to right shift the intermediate result v by 4 times k. At each iteration, instead of a long right shift, we can just pick the usual reciprocal result, or, alternatively, the hex shift variant, and then either way, just align byte by byte to achieve the overall 4 times k right shift effect. We can also pull a similar trick to pick up a reciprocal result that is left shifted 1 or 2 places to achieve a 2 over 125 and 4 over 125 without subsequent long shifting. For now though, we'll leave our pseudocode as is in terms of the 4 times k, but come implementation time, we'll be making full use of these reciprocal shifting tricks. Last thing we do want to change on the pseudocode though is the length of the k loop. Our long reciprocal approach works well until the last iteration of k, at k equals 16, by which point we're calculating reciprocals of 129, 132, 133 and 135, all 9-bit numbers allowing for the added sign bit. But it turned out the last iteration didn't make a difference to the overall result, so we dropped the last iteration, meaning the final reciprocals are 121, 124, 125 and 126, and therefore fit in 7 bits or 8 bits with a sign bit added, and, as always, 8 bits is the magical number when doing anything on my relay computer. Okay, aside complete, let's get back to the monstrosity of a flowchart. The good news is we've already done the hard bit for all of this, which is adapting the standard non-restoring division approach to fit within the confines of my relay computer. Mostly that's been working around the limited availability of registers, but also lots of junk ALU operations to set flags. Now that's actually something I might consider as a future improvement for my relay computer, to perform an ALU operation but skip loading register A or D. With that, the ALU flags will be set as needed, but there's no register mutation going on. As usual, the challenge in setting that up is in the opcode design and fitting everything within an 8-bit instruction, but that's one for the future to-do list. For now though, we've got what we've got in terms of relay computer, so let's get this coded up. As always, I'll be writing this in my custom assembly language and using my custom IDE, which is available at editor.relaycomputer.co.uk if you'd like to play along. And of course, the resulting code will be available under the import menu's examples by the time this episode goes out. Anyhow, here's a starting comment block which explains what we're trying to achieve, and as you can see, I'm still going with the 1 divided by 125 example. However, I'm pushing the boat out and calculating to 10 bytes this time, as that'll give us a good feel for expected runtime. To keep track of things, you can also see I've got the flowchart at the right for reference, and the relay state example we spent plenty of time on last episode. Right, first things first, I need to reserve some space for the result, and I'll use the label RA to refer to that location. We'll want 10 bytes, and I'll initialize each byte to hex 11. That's not strictly necessary, but it just helps when looking at things in the emulator here, and then you can see where the result will appear. Now, as I've mentioned before, everything in memory is just ones and zeros to the relay computer, and currently, if we run the program, it's going to take those hex 11s as instructions. We don't want that, so we'll jump over the data like so. I think then, just for aesthetic reasons, we'll also pad out a further 3 bytes so the result sits nicely in the emulator. Again, none of this is necessary for the relay computer itself. It doesn't much care where we place the result in memory, although we do need to be within the 0 page because we'll be stashing the negative divisor in M1. Right, let's get our setup phase coded up. And firstly we need to load M1 with a divisor and M2 with the start address. We can do that with my custom pack operator, which will take the literal 125 and the 0 page address of RA and smush them into a single 16-bit value. Here in the assembled output you can see the 125 as 7D in hex in the first byte, and then 06 in the second byte, which is the current address of label RA, and is where our result should start in memory. Next we load register B with 10, which is our desired byte length for the result. Then we need to stash our positive and negative divisors and stop address. We copy our divisor in M1 over to X, and then for the stop address we take the start address in M2 over to C, add it with B over to D, and copy D to Y. As such, Y now references the byte immediately following the 10 bytes of our result. To calculate the negative divisor, we copy X to B, logic not to D, copy that back to B, and increment to D. That's then the 2's complement of the divisor, and we'll place that in M1. Next we need to set the accumulator A to 1, clear flags, and set the sentinel bit in D. To do that we'll load B with 0, increment A, and copy A to D. Right, that's setup done. And we're now ready for our inner and outer loops, and I'll add labels for each. First we have our A loop, which is the byte by byte outer loop. We then have our B loop, which is the bit by bit inner loop. The labels are of course pointing to the exact same location in memory, but I'll keep them separate to keep the inner and outer loop distinction. Okay, we're now in the inner loop, and first job is to test the sign bit. We'll use the BMI mnemonic to branch if minus, that is if the sign bit is set. We could have also used the synonym BLT, branch if less than, which results in the exact same F0 opcode. Typically though we'd use BLT following subtracting one number from another, and BMI if we're checking if an ALU result is negative. Very similar, but slightly different intentions. Anyhow, if the last ALU operation set the sign flag, then we're adding the divisor, and we'll jump to an add label. If not, then we'll drop through to subtract the divisor. I'll still mark this with a label though, just to make the intention clear, but it's only there for our benefit and not referenced otherwise. In the subtract branch, we left shift A first, which we'll do by adding it to itself, therefore multiplying by 2. Then we can copy over the negated divisor in M1 and add together to register A. In the adding branch we similarly begin by left shifting A. And the reason we duplicate the code from the subtract branch is because performing the shift would change the ALU flags, so we need to make the jump beforehand. As always, there's trade-offs with these sort of things, and here we're accepting an element of duplication for overall execution simplicity. Memory traded for runtime. Our positive divisor is in register X, so we bring that over and add to the accumulator A. Right, we're ready for deciding the next quotient bit, but before we do, I need to ensure the subtract branch doesn't run into the addition branch, so I'll create a set label here, and then jump over the addition code at the end of the subtraction. Cool. So I think I'll deviate slightly from the logic diagram here and clear C first, and then jump over if the addition or subtraction set the sign flag. If the sign flag was clear, then we load B with 1 via a set AB instruction and copy that over to C. Again, that means an otherwise unnecessary 8 cycles when the sign flag is clear, but it makes the code flow a bit better. We can now test the sentinel bit for exiting the inner loop. And to do that, we'll perform a junk ALU operation. Here, a logic core is as good as anything else, and in all cases, the price of updating the sign flag is that D is now considered mutated, and register B then contains our true quotient. If the sign bit is set, then we can exit the inner loop, and for now I'll add the label so everything assembles. If we're sign clear, then we're heading for another inner loop, and we need to apply the decided quotient bit, which we'll do by rotating B into D, copy back, and then add B and C into D. Finally, in preparation for the next iteration, we set the sign flag for A through another junk ALU operation. That mutates register A, so we copy B back to A, and we're good to unconditionally jump to the start of the B loop. We're now ready to implement the inner loop off ramp, and this is where it gets a bit fiddly, as we need to apply the final quotient bit in register C, but we also need to skirt around the sentinel bit that's allowed us to exit the inner loop in the first place. So we rotate our true quotient in B over to D, and that will now be correct for the leading 7 bits of the byte. In the least significant bit of the byte, however, we've now got the rotated sentinel bit. Nonetheless, we add our final quotient bit in C to it, and now our result is going to be 1 more than we want, so we load B with -1 and add that back to D to decrement D. And now our quotient byte is as expected, and we can store the quotient byte. To do that, we need to preserve our negative divisor in C, and then we can clear M1, so M as a whole is now pointing at the next 0-page result byte in memory. We then store the quotation byte held in D, and restore the negative divisor back to M1. Next, we increment M2 to point at the next location in memory, and we can then take that incremented location and the stop address in Y and perform a logic exclusive OR, which will set the 0 flag if the values in B and C are the same. As such, if the 0 flag was set, we jump to done via BEQ, branch if equal. Right, nearly there. If we're going for another byte, then we need to initialize the sentinel bit again in register D, and then update the sign flag for the current accumulator in A with another junk operation. This time we'll use an ALU increment, and again that'll mutate A, so we restore A from B. And that's it, and we can unconditionally jump to the start of the outer A loop. Finally, as a bit of developer convenience, we'll load register M with a full 16-bit address of the result. This is handy in the emulator, but also for a change, this will be handy on the relay computer too, as we can then use the M register to find the start of the result and start stepping through it. With that done, we're good to halt. And that's it. That's the full flowchart covered and a full implementation of a long reciprocal via non-restoring binary division. Let's give it a run in the emulator, which looks like it's taking a bit of effort this time. And there's the result as expected. Marvellous. Just before we move on and declare the code complete, in my opinion, this code is a bit light on comments, and unless you'd had this first-hand walkthrough and explanation of the code, it could be difficult to understand why things are done a certain way and what the developer was thinking when coding this all up. For modern languages like Microsoft C#, you can arguably keep your comments a bit higher level, as, assuming the code is well written and intent is clear, then code self-documents to a degree. Here in assembly land, that's not the case, and you'd have a hard time understanding what the code is supposed to be doing from the mnemonics alone. As such, it's worth putting in a bit more effort with the comments in assembly, and if you load this example from the import menu, you're going to see something more along these lines. Functionally, this code is identical to what I've just written, but now we have much more commentary going on, explaining the process and, quite handily I find, what state the computer is likely to be in at key points. This can be useful in debugging, as you can place a halt command wherever you like and inspect the computer's state both in the emulator and real thing. Anyhow, to prove this isn't all smoke and mirrors, let's rerun the code. and we get the same result. And we also get the same runtime of 28 minutes, 26 seconds. Wow, nearly half an hour just for a single 10-byte reciprocal. That's not looking promising. Okay, just for giggles, let's see what that would mean for the overall BBP pi calculation. So let's bring in the updated pseudo code from earlier, and we'll focus on the four fractions A, B, C and D. There's many other operations in the pseudocode of course, but let's assume the reciprocals are going to be the main driver of total runtime. So 4 long reciprocals, and there's 16 k-loop iterations in total, so that's 64 long reciprocals, and as we know now, each 10-byte reciprocal takes 20,482 cycles to complete, so adding all that together, we're looking at 1,310,848 cycles. How quickly we can chomp through that is pretty much a function of clock speed, but let's assume the default of 6 Hz, which is equivalent to 12 cycles per second, and so taking all of that together, the 64 long reciprocals, and our minimum total runtime would be 30 hours, 20 minutes, and 38 seconds. Definitely room for improvement then. But where to start? Well, I think I mentioned this before, but I'm a software engineer by trade. So there's a couple of places I'd instinctively start looking, but I'm also interested in your thoughts in the comments. Did you spot the same things I did, or are there some other improvements you think I could make? Firstly then, I reckon I might have fallen into the trap of premature optimisation. And here's where I think it happened. If you're not familiar with the phrase, premature optimisation is spending a lot of time on something you may not actually need. It's the constant danger if you're that sort of developer, and I am, and if I was doing this again, I'd probably have written restoring division first before moving on to non-restoring so that I had a baseline for comparing the two speed-wise. And actually, when you read upon these division approaches, it's usually made quite clear that non-restoring's improvements are very much architecture dependent. And that's where I've fallen foul here. So why is that? Well, typically a computer uses an accumulator in arithmetic operations. So to perform 2 plus 1, you'd start with 2 in the accumulator A and 1 in another register or somewhere in memory, and then in a single operation you'd add those together back into the accumulator, which would then overwrite the previous value of 2 with 3. Now ordinarily that's a good thing as it's very efficient, but this is why the restore step is needed in restoring division. We have to undo the subtraction if the result is negative. So how does that compare to my relay computer? Well, in our case, the only way into the ALU is via the B and C register, and the ALU is permanently connected to whatever is in those two registers. To simplify the hardware design, there's no clever buffering or gating, and that ultimately means you can't load a result into B or C whilst reading those registers during an ALU operation. Bad things would happen. As such, that's why the ALU instructions can only load A or D. So for our simple addition example, we'd have to copy the 2 from A into B and then add back to A. Notionally we end in the same register A state, but it took more faff to get there. For us then, the restoring part of restoring division doesn't mean re-adding the subtracted divisor. We can just copy B to A instead, and that's the restore done. As such, I have a sneaking suspicion restoring is actually going to be quite a bit quicker than the oh-so-clever non-restoring approach, which is certainly more sophisticated, but might actually be more than I need. A premature optimisation on my part. Anyhow, this is all part and parcel of coding, so let's see what that does to our flowchart. So let's jump straight in, and we can start here. And currently we make a decision based on the sign flag and add the divisor if set and subtract the divisor if clear. Well, we can simplify that, as we'll always be trial subtracting the divisor now, and that also means we don't need two versions of the divisor anymore. As such, we'll still negate the divisor in the setup phase, but store that in X instead, which frees up register M1 like so. Also, because we're no longer testing the sign flag before subtraction, we don't need to update it at the end of the inner and outer loop, so we can optimise there too and skip the junk ALU operations. The only bit we then need to add is after the subtract divisor step, where we restore A if the subtraction resulted in a negative value, and we can simply do that by copying B back to A, effectively restoring A. And that should be it, I think. Right, let's head back to the code and make the changes and see what impact it has. Okay, here's where we left off with the non-restoring reciprocal code, and this is the version with loads of comments, but otherwise functionally equivalent to what we built up line by line. Before we make any changes, let's give the current code a run and make sure it still works. But what I'll do this time though is tweak the emulator settings here and change the IPR, instruction per UI refresh, to 4. That way the emulator will update the display every 4th instruction, and that'll make things a little bit quicker to watch, even though the underlying emulation is exactly as before. So let's click run. And we get the expected results and the expected 2826 runtime. Right, let's take out the add divisor branch here. And then the BMI above can come out too, as we'll always be subtracting. And then there's no need for the jump to set, we can just flow through. Finally, let's update the comments for what we've just changed. And if we run the code now, it's broken, but that's because I haven't added the restore operation. Okay, this is going to need a bit of rearranging here then. So we'll start by taking out the subt label, as the trial subtraction always happens now, and then following subtraction we can BMI to a new neg label, where we'll restore the remainder and clear C. Okay, a bit more faffing with comments. Cool. And we restore A from B, and clear C with the CLR clear mnemonic, which is a synonym for move CC, that is, copying C to itself, which effectively clears the register. That can then flow through to the set label when done. If the sign flag wasn't set, then we'll load B with 1. Then copy that over to C, and then jump over to set. Cool, let's give that a run. And runtime has actually gone up by a couple of minutes. Let's plow on though, as the changes so far mean we can now implement our other savings. We no longer need the sign flag updated before the A loop, as we'll always trial subtract, so we can drop the 3 lines at the end of the A loop here. And I'll update the comments again, of course. We can also update the sign flag as part of the setup phase, although here, we can load A with 1, and then copy that to D. Let's run again. 2954. Okay, about a minute and a half longer than non-restoring, which is fair enough, as we've mostly fiddled with the outer loop. Must be something I've missed in the inner loop. Ah yes, here we go. I've got duplication of the quotient bit logic. Let's pull that out. And running again. 2528. That's better. A 3-minute saving over non-restoring. This just reinforces again how anything within a loop of a loop is likely to have a greater impact on runtime. Right, I think the only other thing we wanted to sort was only needing the negated divisor. So we'll be putting the negated divisor in X now. So that's a move from D to X rather than M1. And then let's look for where M1 appears and update those where needed. Okay, quite a few comments to update, but that's fine. Oh yeah, we don't need to preserve M1 anymore, as it'll always be 0 now, so let's sort that out too. Cool, and then there's one more comment to update. Yeah. Just need to make sure M1 is cleared before we go into the A loop too, of course, because we're using M1 to load the divisor. Okay, let's run. And that's 25 minutes and 8 seconds. So a further 20 second saving, which is fine as that was outside the loop, so I wasn't expecting a massive impact. Right, so we've converted to restoring division. Let's check what that's done for the overall runtime. And there's a demonstration that small optimisations can make a big difference in the long run. 3.5 hours shaved off the minimum Pi runtime. 26 hours is still a long time to wait for something though, so maybe there's more we can do. Something that comes to mind is those loops within loops again. Jumps in my computer are relatively expensive at 24 cycles each, and when you've got an inner loop doing 8 of those per iteration, and with 10 bytes per reciprocal, that's 80 jumps and 1920 cycles in total. So just over 10% of the restoring reciprocal runtime. That's going to be worth a look. Let's start with a simplified example of what I think might help out. Here's the Fibonacci series again, which was last seen in my Turing completion episode. This technically uses a while loop where we just keep going until something happens. In this case, we're looking for the carry flag being set. Let's run the code. 2 minutes, 7 seconds. So pretty quick already, yeah? What's interesting here though is that the carry flag will always be set at a deterministic point, after 13 iterations. That means we could also write this as a for loop counting from 0 to 12. But surely the while loop is more efficient, I hear you cry. And yes, you're right, because a while loop doesn't need a loop counter. But I think I've got a trick up my sleeve. I'm going to unroll the loop. And bear with me, this is going to look a bit crazy to begin with, but what I'm going to do is this. And there we go. Exact same output. But runtime is nearly half, with 2 minutes 7 down to 1 minute 17. So we've traded code duplication and memory for runtime. This approach is called loop unrolling because we, well, unrolled the loop. And doing so can have a big impact on runtime if used effectively. Now you could say the cost in developer sanity might not be worth it, but as it happens, there's a nifty trick I've added to my assembler. Watch this. Neat, eh? Same assembled code, same speed gain, but much easier to read. This is the for directive, and it will repeat the enclosed block 13 times when assembling the program. The memory taken up by the assembled program still suffers, of course, but at least between speed, reliability and code size, we're only compromising on one of those now. What's also nice is you can use a looping variable. So here let's do a range, and then I'll load A with I. And in the assembled output, you can see that's been unrolled and I has been substituted in. Right, let's try that on the long reciprocal. So we'll pop in a for directive at the head of the B loop, and then replace a jump at the end of the loop. Rather nicely, the assembly is smart enough to treat those labels as local to the directive, so they'll all work out in the assembled code. Speaking of which, that's got quite a bit longer, of course. So last line is hex 0110, that's 272 bytes then. But let's see what that's done for runtime. We're down to just under 23 minutes now, and have shaved off another 2 minutes 20 seconds. Let's quickly add that to the scoreboard. Oh yeah, now we're cooking. That's just over 6 hours saving versus the original approach, and we're close to a single day runtime. Now, don't forget, that's just for the reciprocals, and now we're paring those down, the long additions and subtractions will have more time impact than before, but still, it's looking much better. Goody good good. Right, I think there's one more thing I want to try out on this episode before we call time, so back to the flowchart. And actually it doesn't look particularly different, and that's because loop unrolling doesn't change the high level logic or flow, it's all down at assembler level. What unrolling does open the door to though is getting rid of that pesky sentinel bit testing. We don't need that anymore because we'll repeat the B loop exactly 8 times. So let's drop the sentinel bit test, and our flowchart becomes this, where we loop on the first 7 visits and then exit on the 8th visit. Nothing for us to do there, of course, our for directive provides this free of charge as it were. With that done, there's no sentinel bit to set up or reset at the end of the B loop, and so that gets us here. It also means we can simplify the A loop off ramp, as we don't need to skirt around the sentinel bit anymore. So much so that we can set the quotient bit at the end of the A loop like so. There we go, much simpler. What do you think? Before or after? Before or after. Anyhow, let's get this coded up, and I'll pick up the pace a bit now, but the final code will be available in my IDE if you want to take a closer look at your leisure, of course. Right, off camera I've had a teensy weensy tidy up around the comments and such like, but nothing functional just yet. Although I did spot one gaff down here at the end of the A loop. I've missed taking out the sign flag junk ALU operation. That's got to go. Let's just check then. 2248 before. Take out the junk. Run again. And 2028, which means I've shortchanged restoring by 2 minutes 20. Let's quickly right that wrong. So here are the scores before and after. So restoring was even more of a saving than thought, giving 6 hours back, with loop unrolling continuing to save something like 2.5 hours. Right after that slightly embarrassing oversight, let's see if we can get even more dropping the sentinel bit stuff. So our quotient starts as 0 in setup, and then we can set our next bit just as before, but we can drop the sentinel bit test. Although we need a small tweak here, as the quotient in D isn't mutated by a junk ALU operation anymore, so it's the right value to use. Cool. And then when we drop out of our loop here, our byte will be exactly as needed, so all of this can go. And then before we loop for the next byte, we need to clear the quotient. Right, that should do it, and runtime is 16 minutes and 29 seconds. Awesome. So here are the final scores with our latest run on the right, and I hope that pretty well demonstrates not only the perils of pre-optimization, but the joy of post-optimization. All that said though, we shouldn't get too self-congratulatory here. 17.5 hours is still an eye-watering runtime, and that's before we add on the rest of the BBP pi calculation. And besides, it's worth noting that although we've managed to squeeze some speed out of the long reciprocal routine here, the restoring approach is still considered a very slow way of doing division, and there are faster, but more complicated approaches out there. Now, I have looked at some of them, but admittedly not got my head around them yet. However, if you think I'm missing a trick here, please do comment below. I'd be delighted to know your thoughts and ideas for a way forward. In the meantime though, without wanting to prematurely disappoint anyone, these numbers aren't looking promising for achieving pi on my relay computer. Yes, it's theoretically possible, and I'm pretty sure I'll be able to prove it out in the emulator, but unless I can get those times down, I'm not keen on leaving my relay computer running all day. Not that it'll catch fire or anything, but it would be a real test of reliability and endurance. Anyhow, we'll see, and with that bombshell, I'll end this episode. And next time, more positively, I'm going to write the full BBP pi calculation in assembly. You lucky people, you. For now though, thanks for watching and for sticking it out in this mammoth 2-part episode, and as always, I'll see you next time.